Hello class, in this video we cover section 11.7, events involving and conditional probability. So the focus of this section is multiplication rule. You might remember in previous section we have learned an addition rule. So addition rule is to find the probability of A or B. And today we are going to learn a multiplication rule. Multiplication rule has two formulas as well, and we are going to apply the multiplication rule to compute the probability of A and B. So that's the task of this section, all right? This is the task of this section. We have two formulas to select from whenever we need to find the probability of A and B. The first formula, P of A and B equal to P of A times P of B. But this formula only holds when A and B are independent. What is independent? We will take time to understand that concept in a moment. When the two events A and B are independent, then the probability of A and B simply equal to the multiplication. That's the reason the rule is called a multiplication rule, right? Equal to the multiplication of P of A and P of B. What if the two events are not independent? Instead, A and B are dependent. Then the probability of A and B would be found by using this formula. P of A times P of B given A, or equal to P of B times P of A given B. Which one depends on which event occurs first. All right, one of the two things, either this one or this one. So make it simple, I'll just erase one of the formula. All right, we have two formulas to apply when it comes to computing the value for probability of A and B. And both of the two formulas together is called the multiplication rule. And this probability, as you can see, P of B given A, this is how do we announce the notation. P of B given A. There's two events, A and B, and A is the event occur first, and then B occur after A. And we use a short vertical bar to separate the two events. The way we say this notation is probability of B given A. This is a conditional probability, okay? This is a conditional probability. The name of the probability is very intuitive. What is conditional probability? Conditional probability is a probability with a condition. What condition? The condition is A already occurred. So this probability, P of B given A, represents the chance of event B occurring given the condition that event A has already occurred. Does that make sense? The name is very intuitive. The notation is also very intuitive. Whatever behind the bar, next to the right of the bar, that's the event it already occurred. We consider the chance of B occurring under the condition that A already occurred. So this would be different from P of B, unless A and B are independent. So we're going to talk about that in a moment. All right. How about let me give you a very simple example to explain what is the conditional probability, and you can see the difference between a conditional probability and a regular probability. Let's think about rolling a die. Very simple experiment, classical model. Rolling a die, and the sample space contains 6 outcomes. Either you got the number 1 or 2 or 3 or 4 or 5 or 6, right? And then we let A to be the event that you get an even number. and we let B to be the event, that you get the number 6. And we are going to consider the following two probabilities. The first probability is P of B. The second probability is P of B given A. Yeah, this is the normal probability. This is a conditional probability. Let's see what's the difference between them. Okay, so we roll a die one time. And what's the probability of getting a number 6? Since number 6 is one outcome, right? So the probability is 1 over 6 in the classical model. And let's look at this probability, P of B given A. P of B given A. Let's explain the meaning of this notation one more time. P of B given A refers to a conditional probability. It is the probability of B occurring under the condition that A already occurred. In this specific case, P of B given A represents the probability that we get a number 6, given the condition that we already know the number is an even number. Yeah, we already know the number is an even number. That means what? That means you will not consider 1, you will not consider 3, you will not consider 5, because they are not even. In other words, when we consider the event A already occurred, we already know the number is an even number. Your sample space shrunk. You're going to have a smaller sample space. In the new sample space, we only have 3 outcomes, all the possible outcomes. Under the condition that A already occurred, we already know the number we got is an even number. So the sample space is not the original sample space anymore. It's a restricted sample space, as the book states, or shrunk sample space, smaller size. In this case, containing 3 outcomes, 2 or 4, 2, 4, and 6. Do you see that? So when you attach a condition, normally when you attach a condition, the sample space will get smaller. So this is a new sample space. In that sample space, the probability you get a number 6. Number 6 is one of the 3 outcomes. We got a 1 over 3. So you can see the meaning of those two probabilities are different. The value turns out are different as well. I hope through this simple example you can understand the definition of a conditional probability. Also see the difference between a regular probability and a conditional probability. I would say some students think it's challenging, but actually it's not that challenging. All you need to do is to consider the condition, right? Yeah, knowing event A already happened. So the setting of the whole experiment is different. Your sample space will be smaller, but it is still a classical model. All right, so let's go back our guided note. Also, I need to double check. I am recording. I'm not muted, and I am sharing. Okay, so let's go back our guided notes here. The first concept in this note is independent. It is the concept of independent. We mentioned that earlier here, right? Yeah, we have two formulas in the multiplication rule. The formula to compute the P of A and B when the two events are independent is quite simple. Just multiply the two events, right? Multiply the probabilities of two events. And that formula only is true when A and B are independent. Now, what is independent? A and B, two events are independent if one of the events occurring does not affect the probability of the other event occurring. So the formal definition is here. Two events are independent events if the occurrence of either of them has no effect on the probability of the other. So they do not affect each other. They do not affect each other. Occurrence chance-wise, they do not affect each other. If two events are not independent, then we say they are dependent. So those are the two things. the focus of this chapter, this section is to find the probability of A and B, right? So whenever we need to find the value for P of A and B, the first thing we need to do is to determine, are the two events independent or dependent? If they are independent, use the first formula. If they are dependent, use the second formula. All right? So let's look at this. Let's look at some examples. Here is a roulette, right? A roulette wheel has 38 numbered slots, 1 through 36, 0 and 00. Of the 38 compartments, 18 are black, 18 are red, and 2 are green. So as I can see, this 00 is green, this 0 is green. And we have 18 red numbers, and we have 18 black numbers. So around the circle, around the wheel, we have 38 slots. That's a roulette wheel. A play has the dealer spin the wheel and a small ball in opposite directions. As the ball slows to stop, it can land with equal probability on any one of the 38 numbered slots. Find the probability of red occurring on 2 consecutive plays. Okay. So my understanding, yeah, read the last sentence. Normally, the last sentence gives us the goal. What are we looking for this specific question, right? It says to find the probability of a red, find the probability of a red occurring on 2 consecutive plays. Means you play twice, right? Yeah. So my understanding is this: if I let A be this event, I will use the quotient. Yeah, A as the this event, what event? The first play gets a red number. Okay, and the B represents the event. The second play, second time or second play gets a red number, right? So what are we looking for? We are looking for the probability of A and B. Do you agree? Properly using the notation to represent the English sentence describing the result is also very important. That's how do you get started at the solution, right? Yeah. Find the probability of a red occurring on 2 consecutive plays. So you have 2 plays, first play, second play. So we are looking for the probability that both of the 2 times we get red numbers. So if we let A be the first time we get a red number, even B be the second time we get a red number, then we are looking for the probability of A and B. Probability of A and B. Remember, when we looking for the probability of A and B, we apply the multiplication rule. And the first thing we need to determine before applying the multiplication rule is to see if the 2 events independent or dependent. What do you think? This is an dependent case or independent case. A and B are what? You pause and think and see if you have the same answer with me. They are independent. The first time you get a number, red number or black number or green number, it does not affect the result of the second time you get I think everything gonna go back to the original setting. That's my understanding of roulette. Right? Yeah. So they are independent. It's like you roll 2 dice in a row, roll a die twice in a row. Then you first time you get a number, and the second time you get another number. Would the first time affect the second time? We do not consider the psychological factor. They do not affect each other, right? And also you toss a coin twice. Would the result from the first time affect the result the second time? No. Yeah, you spin a spinner or you spin the roulette wheel, they do not affect each other. So the 2 plays are independent from each other. So based on that, the formula we're going to apply is P of A times P of B. How do we find the P of A? The probability that we get a red number. The probability we get a red number. So I'm going to use this. Yeah, let me use the formula here. The first time we get a red number. So 38 times numbered slots in total, right? And among the 38 numbered slots, how many of them are red? 18. So 18 over 38. 18 over 38 is a simple classical model, right? It doesn't really help me do it again. Okay, awesome. That's what I want. And that's the probability of A. Multiply probability of B. What's the probability of B? Same, right? Yeah, same thing. Second time you get a number, red number, is still because the ball, a roulette wheel has 38 numbered slots, 1 through 36, of 38 compartments, 18 are black. So a play has the dealer spin the wheel and a small ball in opposite directions. As the ball slows to a stop, it can land with equal probability. Yeah, my understanding, you know what, I never play roulette, so I assume when before the second spin, everything gonna go back to the original position. All right, if you know roulette very well and you said no, it's a different play method, and you let me know. Yeah, my understanding, since it doesn't have extra information, that's how do I make my assumption. It does not have any information saying the first result would affect the second result. So I assume before you play the second time, everything gonna go back to the original setting. That's my understanding. So it would be 18 over 38 times 18 over 38. And you figure out the result by yourself, okay? Yeah. Reduce. Many of the questions, if you provide all the questions in MATLAB Math, including the quizzes and tests, if you provide the answer as a fraction, the fraction must be simplified. So that's an independent example. Yeah, independent example. Now let's look at this question, this example. The picture above shows a family that had 9 girls in a row. Find the probability of this occurrence. That's interesting, right? Okay. You know, it might be more complicated than we could imagine, like genetically or biologically, and we do not consider those factors. We assume all those 9 births are independent. The first time the mom has a girl or a boy does not affect the second time she has a girl or boy. Yeah, all the 9 events, okay, are independent. Yeah, all the 9 births are independent when it comes to having a girl or a boy. Okay, this is also independent case. You know, we can generalize. Where's my OneNote? Did I close it by accident? Yeah, we can generalize the multiplication rule, the first formula, in the case of events are independent. Yeah, the formula only involves 2 events. But what if we have more events, like we have 9 events, right? Yeah, if we let the first event be the first birth is a girl, and the second event be the second event is a girl, right? Yeah, normally I do this. Yeah, I do this. Let A sub I the event, the ith time get a girl, right? Yeah, and I equals 1 all the way to 9. Then A1, A2, all the way to A9. They are all independent. So by the multiplication rule, the probability of all the 9 times the girls is going to be P of A sub 1 times P of A sub 2 times P of A sub 3 times all the way to P of A sub 9. So the first time going to go half. Second time going to go half. 50% chance, right? Yeah, half times half times half all the way to the last half. So half to the power of 9. And you figure out the value. Yeah, this is also an independent example, yeah, to help us to understand the concept of independent. Next example, the probability that a region prone to flooding will flood in any single year is 1 over 10. The probability that a region tend to flooding will flood in any single year is 1 over 10. What's the probability of a flood 2 years in a row? Okay, so we assume they are independent, okay? And that last year is flooded already, then this year doesn't flood? I don't think so. So we assume they are independent. Then flood 2 years in a row. First year flood, second year flood. So the probability is 1 over 100, well 0.01, right? Part B, what's the probability of flooding in 3 consecutive years? First year flood, second year flood, third year flood. So you get a 1 over 1,000. Part C, what's the probability of no flooding for 10 consecutive years? No flooding for 10 consecutive years. So the first year, no flooding. If the probability of flooding is 1 over 10, then what's the probability not flooding? 9 over 10, right? Did we learn complement the other day, the previous section? Yeah, what's the probability of no flooding for 10 consecutive years? That means the first year, no flooding, 9 over 10. Second year, no flooding, 9 over 10. Third year, no flooding, 9 over 10. Yeah, you're going to write 10 of those, right? Yeah, to make it easier, we know repeated multiplication is an exponentiation. We just raise 9 over 10 to the power of 10, and you figure out the result by using calculator. Okay? And with that, we are able to understand the following concept, or I would see that as a new topic. What topic? Probability of at least one. Probability of at least one. In a case that all those events are independent. Probability of event happening at least one time is equal to 1 minus the probability of event does not happen. So part D, what's the probability of flooding at least once in the next 10 years? If we do not have the formula in the box above part D, well, then we consider the event that over the 10 years, the flood at least one time. That's going to be very complicated, right? Because over the 10 years, flooding at least once includes exactly once. And exactly once could be any one of the 10 years. And also could include the case that the flooding happened exactly twice. Yeah, any of the 2 years among the 10 years, or exactly 3 times, or exactly 4 times, exactly 5 times, 7, 6, 7, is many cases. Do you see what I'm talking about? If we directly to compute the probability, to find the probability of flooding at least once over the 10 years, it's going to be many cases to consider, not convenient at all. So we want to consider the complement. What's the complement of at least once over the 10 years, over the 10 consecutive years? Yeah, so if we let x be the number of flooding in the 10 years, okay, then possible values of x would be 0, no flooding at all over 10 years, or exactly 1 time, or exactly 2 times, or 3, 4, 5, 6, 7, 8, 9, 10, right? Exactly 10 times. Yeah, sounds horrible. All the 10 years flooding every single year. And so that's all the possible values for x, right? If we let x be the number of flooding in the next 10 years, Yeah, number of years flooding in the next 10 years. And the probability we are trying to figure out is the probability the flooding at least one time. So we are looking for probability of x bigger than or equal to 1. And that includes all those at least 1. Exactly 1, exactly 2, exactly 3, all the way exactly 10, right? And what is the complement? The complement is none, no flooding. Do you see that? Right? All the possible values for x are the 11 numbers, 0 all the way to 10. And we are looking for the probability that x is bigger than or equal to 10, that I had it in yellow. Then the complement would be x equals 0, no flood at all. None of the years has a flooding. So we can find the probability of no flooding and then use 1 to minus the probability of no flooding over 10 years. And the result would be at least once flooding in the next 10 years. All right. So in part C, we already have the probability of no flooding. Then part D, is just the probability of the complement of part C. So part D, the answer is 1 minus 9 over 10 to the power of 10. All right. Repeat this part. If I go over too fast, if I went over too fast, repeat this part. It's pretty important. You're going to see a few problems in MATLAB Math about finding the probability of at least 1. Knowing the probability of at least 1 is 1 minus the probability of none. All right, let's proceed. Within a box of 20 assorted chocolates, 5 of them are chocolate-covered cherries. All the chocolates are shaped exactly alike, and it is impossible to tell what is inside each piece. So we don't know the inside. They all look the same, right? Yeah, 20 chocolates, a box of 20 chocolates. 5 of them are cherry flavor. I would say it's cherry flavor. And you want to know what your chances. So this is an example, right? So we have the answer already provided. Yeah, we can, since we already started, we can continue. So you want to know what your chances are of selecting 2 cherries flavored chocolates. Since 5 of the 20 pieces are chocolate covered cherries, the probability of getting 1 on your first selection is 5 over 20, right? Now suppose that you did choose a cherry flavor on your first try. There are now only 19 pieces chocolate left, and only 4 of them are cherry flavored. So the probability of getting the second cherry flavor would be 4 over 19. Do you see that is an example of dependent. The first time getting a cherry or not getting a cherry directly affects the probability of the occurrence of the second time getting a cherry or not getting a cherry. So that is an example, good example of dependent. They are not independent. 2 events are dependent if the occurrence of one has an effect on the probability of the other. Okay, yeah. So this actually is the formula I gave you earlier in my note right here. The second formula of the multiplication rule. We understand that formula by using it. Okay, the probability of selecting 2 chocolate-covered cherries in a row. I want you to relate the multiplication rule with the fundamental counting principle. So we are looking for the probability that the first time get a cherry, second time also get a cherry. Okay, by the fundamental counting principle, the first time we get a cherry, probability is 1 over 4, right? Yeah, and then multiply by fundamental counting principle is multiplying, right? Multiply by the second time also get a cherry. But since the first time you already took a chocolate, you only have 19 in total now. and among the 19 of the chocolates, you only have 4 of them are cherry flavor. So times 4 over 19. So I would recommend you think about, when you apply the multiplication rule, you are thinking about fundamental counting principle. All right, this is an example that we need a practice. Let's look at this problem. You won a free trip. You won a free trip to Spain and can take 2 people with you. All expenses paid. 10 of your friends are begging you to take them. It's going to be make you feel very important now. You write each friend's name on a card. Place the cards in a hat and select one name. Then you select a second name. Yeah, that's how you process the experiment. You get all the 10 names in a hat, and then you're going to do twice. The first time so this is without replacement. Very important. With replacement is independent. Without replacement is dependent. Okay, without the replacement is dependent. At least you can see, without the replacement, when you take the second name, you do not have 20 names in the hat anymore. You only have 19 left. So obviously it's dependent. So this is dependent. Then you select the second name without replacing the first card. If 3 of your 10 friends speak Spanish, find the probability of selecting 2 Spanish-speaking friends. Okay, so A is the first time we get a Spanish-speaking friend. Okay, Spanish-speaking friend. B is the second time you select a Spanish-speaking friend. All right, so we are looking for probability of A and B, and we are going to think about fundamental counting principle, right? Fundamental counting principle. Okay, the first time you get a Spanish-speaking friend, so you have how many? 10. You have 10 friends to select. How many of them speak Spanish? 3. So the chance of getting a Spanish-speaking friend of the first time at the first time is 3 over 10, right? Yeah, think about fundamental counting principle. That's the first step of the task. Selecting a Spanish-speaking friend the first time, 3 over 10. And then multiply, yeah, the second step. The second time you also get a Spanish-speaking friend. But when you picking the cards in the hat, you do not have 10 cards anymore. You only have 9 cards left. And among the 9 cards, you only have 2 representing Spanish-speaking friends. Does that make sense? Because you already throw away a card. So you only have 9 friends left. Among the 9 friends, you only have 2 friends speak Spanish because you already picked one, right? So that's 3 over 10 times 3 over 10 times 2 over 9. Butterfly method, 2 and 10 has a GCF 2, so 2 becomes 1, 10 becomes 5, and our result is 3 over 45. Oh, actually, my bad. This is 3 becomes 1. Yeah, another butterfly diagonal direction. 3 becomes 1, 9 becomes 3. So we have 1 over 15. 1 over 15. The reason you need to take algebra before taking this class is because the calculation part uses algebra knowledge. All right, so that is a very good example about finding the probability of A and B. In the case of A and B are not independent, they are dependent. Then I would recommend you try thinking of try to think of the fundamental counting principle. So 2 steps. Yeah, the first step is to pick the first Spanish speaking friend, right? So the chance is 3/10. Multiply by second step. Yeah, pick another Spanish speaking friend. However, you only have 9 friends left. Among the 9 friends, you only have 2 of them. Two of the friends speak Spanish. Conditional probability. I explained the definition of conditional probability, right? This is a conditional probability. What is? This is. You might not even aware of that. You might not even aware of that. But that is a conditional because you assume the first time you assume the first time get a Spanish speaking friends already. Okay, so when you apply the fundamental counting principle, sometimes you are not even thinking of the conditional, but you are actually, the second probability is a conditional. Next example, you are dealt 1 card from a 52 card deck. We have 2 parts to answer. Part A, find the probability of getting a heart, given that the card you were dealt is a red card. So part A is to find a probability, conditional probability, right? Conditional probability. Now I would properly denote the probability. Finding the probability of getting a heart. Let me draw a heart. Given, you draw a vertical bar, right? Given it is a red, you already know it's a red card, right? Red card. I have to use a red color, but a little bit troublesome. So the probability of getting a heart, given that the card you were dealt is a red card. Remember, when you consider conditional probability, your original sample space shrunk. Original sample space is are the 52 cards, right? In a deck. Since now you attach a condition when you consider the probability, you attach a condition. What condition? You know the cards you get is a red card already. So half of them are red, the other half are black, right? So we have 26 red cards. So your sample space shrunk to a sample space to a set containing those 26 red cards. 13 are from the hearts, red hearts. The other 13 are the red diamonds. Okay, so your denominator is not 52 anymore. Your denominator is 26. Among the 26 red cards, how many of them are hearts? I mentioned 13 of them are hearts, right? Yeah, so the probability is half. Part B, find the probability of getting a red card given that the card you were dealt is a heart. It's interesting. We're interested because it switched the order of the 2 events. This time the condition is not getting a red card. The condition is getting a heart. Okay, so your original sample space contains all the 52 cards, right? But now you attach the condition. What condition? Your card was a heart. How many of them are hearts? 13 of them are hearts. So your new sample space is the sample space containing the heart soup, yeah, all the 13 heart cards. So your denominator is not 52 anymore, is 13. Among the 13 heart cards, how many of them are red? How many of them are red? I think all of them are red, right? Have you ever seen a black heart? Yeah, all the hearts are red, all the diamonds are red, all the spades are black, all the clubs are black. So among all the hearts, they're all red. So 13 of them are red. So it's 1. Yeah, suppose you already know your card is a heart. Then what's the probability that the heart is a red card? 100%. Because all the red cards are 100%. As you can see, this question would actually can tell us in general, P of A given B and P of B given A, they are not the same. In general, not the same. Maybe in occasion, for example, they are maybe some coincidence, they might be the same value-wise, but in general, those two probabilities are very different. Those two conditional probabilities are very different. Continue examples. The table below shows the outcome of car accidents in Florida for a recent year by whether the driver wore a seatbelt. Yeah, let's look at the table. Horizontally, we have two rows. Driver survived, driver died. So that's the row by row, right? By columns, we have also two categories: wearing a seatbelt and not wearing a seatbelt, right? So in total, we have this many people. So that's going to be the denominator for empirical probability fraction. Part A, find the probability of not surviving a car accident given that the driver did not wear a seatbelt. Okay, I would do this. Use some keyword to remind myself what is the conditional probability talking about. Find the probability of no surviving, so die, right? Die. No surviving, so died. Given that the driver no seatbelt, no seat belt. Okay, is a conditional probability. So are we still using this as the denominator? No. Our sample space shrunk. Yeah, because we already know the driver did not wear a seatbelt. Did not wear a seatbelt, so our sample space shrunk to this many people. Yeah, those people did not wear a seatbelt. Those people, you would not consider them because they were wearing a seatbelt, right? So the denominator is going to be 164,128. Among those people who did not wear seatbelt, sorry, S-E-A-T, seatbelt, how many of them are dead now? How many of them are dead? This many died, right? 1601. Okay, I'm interested in knowing the value. So let's find the decimal. 1601 divided by 164128. I got I would round it to 0.0098. 0.0098. Yeah, so shy 1%. Very, very close to 1%, but shy 1%. If you do not wear a seatbelt, you have a shy 1% die, right? Part B, find the probability of not wearing a seatbelt given that a driver did not survive a car accident. So this time we are looking for the probability of no seatbelt. No seat belt. Given the driver did not survive. Did not survive means died, right? Died. Okay, in this case, our sample space also shrunk, but since we know the person already died, so we consider this many people as the sample space, right? New sample space, the restricted sample space, or shrunk sample space. Yeah, among those people already died, 2111, among those people who already died, how many of them did not wear a seatbelt? How many of them did not wear a seatbelt? 1601, right? 1601. And this probability going to be huge. Let's do the calculation. 1601 divided by 2111, 76%. we're going to round it up to the nearest whole percent, 76%. So among the people who died in a car accident, more than like around 76%, around 76% of them did not have a seatbelt. So that's how do you understand the situation, right? And yeah, this part explains the restricted sample space. And that's it. Yeah. By going through all the examples in the guided note, we covered all the important concepts. Summarize just very quickly. The focus of today's class is to apply the multiplication rule to find the probability of A and B. And we have two formulas. This formula is the simple version. We only use this formula when the two events are independent. Very simple, right? Yeah, if they are independent, then probability of A and B is just probability of A times probability of B. In the case that the two events are dependent, then probability of A and B would be probability of A, suppose A occurs first, multiplied by probability of B given A. Yeah, under the condition that A already occur. So it's a little complicated, but as I said, the trick is to think of the fundamental counting principle. Knowing when you trying to do the second selection, second trial, the setting changes. Yeah, the sample space shrunk, and the numerator might change as well, right? So consider that. Okay, so you can work on the assignments now, 11.7. If you have any questions, please feel free to email me. I'll see you in the next video. Bye-bye.